Now we will take the other finite 0 type of terms, that is 1 plus st power n. So in your transfer function, if you have a term 1 plus st power n, for that case how to draw the magnitude and phase. The similar analysis we can do, then we can directly plot it. Since it is in the numerator, the graph will be reversed, which means, so till omega c, that is a corner frequency, we have a straight line on 0 dB line where the m is equal to 0, that is mdb is 0 and the slope is also 0. So till this omega c we have like this, then after that there is a change in the magnitude plot. And how it is going to change? Since we have the terms in the numerator, the corresponding slope will be positive, which means we have plus n 20 dB. So plus n 20 dB for decade slope. So therefore the plot will go like this. So from omega c straight line, then after that it increases like this with the slope plus n 20 dB for decade. And as I said, this is the approximate one or asymptotic plot, and exact one follows like this, and at omega t we have the maximum error. That error is plus 3n dB. So plus 3n dB the error for whenever you have the 0 terms, finite 0 terms, and similarly minus 3n dB error for whenever you have finite poles in the transfer function. Similarly the phase plot is also same, whereas it is starting at 0, then it is going to plus n 90 degrees and the shape of the phase plot will be like this. Now the other possibility of having the term is a quadratic factor. Whenever you have quadratic factor, then how to plot the magnitude and the phase. When I say quadratic factor, then the damping ratio of that factor will be in between 0 and 1. If it is greater than 1, we can factorize into 2 factors, and which we can draw as we have seen, but which we cannot factorize, where the zeta value lies between 0 and 1, and my poles will be complex conjugates, roots of complex conjugate, and for that we will see how to plot the magnitude and phase plots. Let us consider the term quadratic factor g of s is equal to omega n square divided by s square plus 2 zeta omega ns plus omega n square. And as we know the first step, we are going to substitute s is equal to j omega. So when you substitute that, j of j omega is omega n square upon, we have s square, therefore that is going to be j omega square plus 2 zeta omega n s, again we have j omega and plus omega n square. So the first term in the denominator is j omega square, that will be the minus omega square, j square will be minus 1. So this is the real part, and also omega n square I have, that is also real part, and imaginary part in the second one 2 zeta omega, again I have j omega, therefore j 2 zeta omega n omega. So when you write this real and imaginary, so it is going to be j of j omega is omega n square the numerator, and denominator I can write it as omega n square minus omega square plus j 2 zeta omega n and omega. Now I can define the normalized frequency in this case. The normalized frequency u is equal to omega by omega n. Omega n is constant. For any given system, the natural frequency is constant, where this omega is independent variable which we are varying. So the frequency is normalized from omega to u by taking the denominator omega n. So when you take that to u, what will be the transfer function? Now j of j omega or j of j u I can call it as is equal to 1 upon 1 minus u square plus j 2 zeta u. Then what is the magnitude mdb? When you take the mdb minus 20 log under root, we have 1 minus u square whole square, a square plus b square plus 4 zeta square omega n square. So what is the phase angle? Phase angle is minus tan inverse. We have 2 zeta u upon 1 minus u square. This is mdb expression, and this is the phase angle expression for the quadratic factor. Now whenever you have the quadratic factor, what will be the corner frequency? Generally for the finite 0 or finite pole, the corner frequency will be either a 0 frequency or the pole frequency. But in this case, for quadratic factor, the corner frequency is the natural frequency of the system. So what will be the natural frequency of the quadratic factor? So what is the natural frequency? Omega n. Therefore, the corner frequency omega c is omega n. Now, again we know what is the meaning of corner frequency. Before the corner frequency, we have one type of graph. Then after the corner frequency, the magnitude plot changes. So omega c is far less than omega n. So in this case, your MdB is going to be 0 and your slope is also 0 dB and phase angle is also 0. Now when omega c is far greater than omega n, then what will be the MdB value? So the MdB is going to be minus 20 log, the formula is same, 1 minus u square whole square plus 2 zeta square u square. And what will be the slope of this? The slope of this is going to be, slope is minus 40 dB for decade. So you are going to get the minus 40 because it is a quadratic term. So quadratic term means there are two time constants, or there are two poles. Those poles are not real poles, they are the complex poles. Whenever you have two poles, then you will get minus 40 dB for decade, which is the slope. So once you have this slope, what are the phase angle expressions? Now you have to be very careful when you are writing phase angle expression for the quadratic factor. So the quadratic factor, when u is very small, then the phase angle is minus tan inverse 2 zeta u, directly we can write it. But when u is very large, then phase angle should be plus, we should take plus tan inverse 2 zeta by u, we have to take it. So we can, if you go back to refer to the phase angle expression, we can do some kind of approximation and we can come up with these two results. One is phase angle is minus tan inverse 2 zeta u for when u is very small value. Similarly, phase angle is plus tan inverse 2 zeta by u, in this case into it is divided by u when the u is very large. You know the u is nothing but the normalized frequency, which is omega by omega n. So when exactly u is 1, what does it mean? Your omega is omega n, your omega is at the corner frequency. So that is nothing but your minus 90 degrees, because tan inverse infinity you will be getting, that is minus 90 degrees. And when you look at the plot, so we know that we have 0 here and the quadratic factor in the denominator, therefore you will get minus 40 dB for decade at the corner frequency. Similarly, we can also draw the exact graph here, and that is the error is going to be minus 6 dB because we have two poles there. Similarly, when you look at the phase plot, in this phase plot it is 0, it is going to minus 180 degrees. So in between you have 90 degrees when u is equal to 1, which means when omega is equal to omega n. So this is for the quadratic factor. The same can be analyzed if at all if the quadratic factor in the numerator and it is just opposite to that, which means we have 0, it is coming up to the corner frequency and it is increasing with a minus 40 dB for decade, and similarly the phase angle also changing from 0 to plus 180 degrees. In between you have 90 degrees at omega is equal to omega c. Then we can summarize all these explanations, analysis into a single table, and if you remember the table, that is enough to solve the problems, to draw the magnitude plot on a semi-log graph sheet. Now what is the summary? So what I am taking is, I am taking the term and also corresponding slope, because slope play very important role in magnitude plot. We know the slope is defined dB for decade. So for 1 decade change in the frequency, how much magnitude in dB is changing, that is the slope, which play very important role when you sketching the magnitude plot or when you want to analyze it. And even though sometimes when you have the magnitude plot, you can find out the transfer function of the open loop transfer function of the system from frequency response. Now the first term, there are three possibilities of the first term. What are the three possibilities? K into s power n, k by s power n. Any one will be there in your transfer function, compulsory. Maybe if k is not there, you will have some constant value. So k is 1, k is 2, k is 3, any constant value. Therefore constant term alone, which means there are no poles at origin, no zeros at origin. And second possibility, constant with you have zeros at origin, maybe 1, 2, 3, 4, any number of zeros, that is k s power n term. The other possibility is k by s power n. So k can be any constant and there are n number of zero poles at origin. So any one will have, I can call these terms as first term possibilities. So whenever you have this, for k, what is the slope? 0 dB for decade. Whenever you have k into s power n, remember I have zeros. Zeros means plus. 0 means always plus. 0 appears in the numerator. Numerator is taken as plus. Therefore, k into s power n, we have plus. And how many number of zeros are? N number of zeros are there. For each zero, there is 20 dB for decade. The result will be plus n 20. Now, k by s power n, denominator minus, there are n number of n, and how many s terms? For each s term, there will be 20 dB for decade. Therefore, the result is minus n 20 dB for decade. 0 dB for decade, plus n 20 dB for decade, minus n 20 dB for decade. So if at all, if you have finite 0, 1 plus st power n, then again same thing. You have n number of zeros at corner frequency. Therefore, plus n 20 dB for decade. Similarly, I have finite poles, 1 divided by 1 plus st power n. Again minus n 20 dB for decade. Then I have the quadratic factor in the denominator. Then it is obviously minus 40 dB for decade. So if you have quadratic factor in the numerator, plus 40 dB for decade. So this is a summary which is very important when you are analyzing the magnitude plot or when you are plotting the magnitude plot. So we need to remember these things.